Hello, today we'll discuss differences between time series and analytical databases and how we improved our time series database at QuestDB. Many of the techniques and optimizations we'll cover today can be met in many modern databases, so the talk should be helpful for anyone who's keen to learn more about analytical databases. My name is Andrei Pechkurov and I work at the QuestDB core team. I enjoy all things around databases, performance, and distributed systems. When I'm not busy with all of that, I love playing board games with my family. Before we go any further, let's try to understand the differences between time series and analytical databases. For the sake of storytelling, we'll use QuestDB as the sample time series database. So, QuestDB is an open source time series database. It combines SQL with high-speed ingestion via the ILP protocol. The data is stored in columnar format, native or Parquet. QuestDB is written in Java mostly, but also in C++ and Rust. When it comes to Java, it uses many techniques that originate from high-frequency trading. Namely, we avoid garbage collection on the hot paths and prefer using in-house APIs over the standard library ones. Other than that, we have vectorized and parallel query engine that also has a JIT compiler. So, what are the specifics of a time series database? Long story short, the database has to be fast for ingestion. In practice, this means a few million rows per second on a single box. And the ingested data is frequently represented on a dashboard of some kind. An important detail here is that the queries usually touch nascent data. For instance, in case of trading, that would be the last few minutes. Lastly, time series databases usually have SQL extensions to simplify the task of querying the recent data. For instance, in QuestDB, we have sample by syntax to provide a convenient way to aggregate data over time intervals. Another syntax that we have is latest on. It allows you to fetch the latest values for each time series. Now, when the time series specifics are clear, let's discuss analytical databases. The majority of them support SQL as a query language, as well as use columnar formats for storage. Their query engines usually involve multi-threading to speed up query execution. When it comes to queries, we're speaking of complex queries with group by, joins, and filters that scan through large volumes of data. And unlike with time series databases, the data is rarely accessed over time slices. So far, it looks like our sample time series database is very, very similar to an analytical one. In fact, a couple years ago, we noticed that some of our users run analytical queries, and a few of them weren't happy with the query performance. So we decided to make QuestDB a faster analytical database, and here our story begins. How does one solve such task? Besides from addressing user requests, we decided to pick up an existing benchmark for analytical databases and improve our results there. There are many available benchmarks, some of which are shown on the slide. And it's important to say that any benchmark should be taken with a grain of salt, and you should measure your specific workload for your application. For us, choosing a benchmark and focusing on it was simply a convenient starting point. We decided to focus on ClickBench since at the time it was recently released and looked relevant. It's created by the ClickHouse team and focused on complex aggregates and filters over a single white table. Some of the benchmark queries access data over time slices, so expectedly, QuestDB was already fast there. But the results in the remaining queries weren't great. Another plus for us is that the published results are collected on AWS EC2 instances, which is a popular choice among our users. So we picked up ClickBench. To be fair, our initial result was pitiful. Partly that's because a few queries were failing due to out-of-memory and SQL errors, but the majority of the queries just ran slowly. After applying the optimizations we're about to cover, we improved our results by 2 orders of magnitude or so. So in the total chart, we went from the bottom arrow to the top ones. This improvement took 2 years. Of course, we didn't focus and didn't work just on these optimizations. In fact, we spent most of the time shipping major features such as write-ahead log or replication. In total, the optimizations took around 80 patches, some of which were community contributed, and some were pretty big. Most of the optimizations can be met in other analytical databases and sometimes serious ones, but some are unique to QuestDB. And as it frequently happens, there were failed experiments on the way. But after all of this, the best part for us is that we have a clear understanding of what needs to be done next. So let's go over these optimizations and see what we've improved. Let's start with the trivial stuff. Some of the ClickBench queries required flavors of SQL functions that were missing in QuestDB. Some of the functions were just too greedy for memory, so we started just with fixing all of that. Next, we already had a just-in-time or JIT compiler for where clause filters. It consists of the backend written in C++ with awesome JIT library and the Java frontend. When you run a query with a filter, it's compiled into a native function to be called on batches of rows to produce the filtered row IDs. When possible, JIT compiler emits vectorized code, so it uses SIMD instructions. And finally, the filter execution is multi-threaded. To improve our results in a few ClickBench queries, we added support for the missing operators and types to the JIT compiler. For instance, initially the filter shown on the slide wasn't JIT compiled, since we lacked is not null operator support for string columns. Another rather trivial but impactful change was to introduce new execution plan rewrites for our query engine. For example, this count distinct query may be rewritten in the following group by form. The later query runs faster since it uses a specialized hash table as well as a JIT compiled filter. Next, we also went through many SQL functions and introduced fast paths for common scenarios. As an example, like operator on short ASCII patterns may be vectorized to avoid scanning and matching characters individually. And we did exactly this for the query on the slide. Another example is the regex replace SQL function. We use regex engine from the standard Java library, but we made sure to avoid garbage when possible. Interestingly is that according to our measurements, the Java engine is pretty fast, on par with available C++ libraries. When it comes to the columnar storage, we had to optimize the way we store strings. To do that, we introduced new varchar type. This type is UTF-8 based and uses layout similar to what Andy Pavlo calls German strings, aka Umbra style strings. Thanks to the string prefix stored in the header vector, equality and other string operators got faster due to better cache locality. Another nice side effect is that we reduced disk footprint for ASCII-only strings. So all of this is nice, but all of this time there was an elephant in the room. Namely, only a few queries of the ClickBench group by once ran multi-threaded. So many of them ran single-threaded. We had a special execution path written in C++, but it was limited to very simple queries, such as those shown on the slide. So we needed a more versatile parallel execution pipeline for aggregations. Before we delve into what we came up with, let's consider a simple query. Here we calculate row counts for each user ID group. Let's think what's the most natural way to process this query. That's simple. We scan rows one by one and absort the counts into a hash table with user ID keys. If there's no key value pair for a given user ID in the hash table, we store 1 as a count, and if there's an existing pair, we simply increment the count. Once we've scanned all rows, we can iterate over the hash table and send its contents back to the database client. All of that executes on a single thread. But how can we go multi-threaded? To do that, we can divide the scanned rows into batches and publish those batches as tasks to be processed by the worker threads. Each worker thread would have its own hash table and do exactly the same thing as what we've just discussed. Once all tasks are processed, we can merge the hash tables produced by the worker threads into the final hash table. Here it's important to say that for many aggregate functions, most of them in fact, the results can be calculated on ranges of the scanned rows and then merged together to produce the final result. Such aggregate functions are called decomposable. In our example, the count function is decomposable since merging partial results for count is as simple as the sum of the partial counts. Congrats! We've just invented a decent parallel execution pipeline for group by queries. A single thread publishes the tasks as the first step. The next step is parallel, and it combines row filtering and aggregation. Finally, the same single thread collects and merges the partial results. In total, there are only 3 steps, simple yet elegant. But there's a flaw in this pipeline. In the high cardinality scenario, say when we have a few 100,000 distinct groups, it won't scale across CPU cores. The merge step is the bottleneck. With so many groups, it becomes too slow and it simply eliminates the speed up from the previous parallel step. Luckily, it's possible to improve the pipeline for the high cardinality scenario. We can use so-called radix partitioning. This algorithm can be met in parallel hash join, but it's also applicable to group by. The idea is simple. We divide all scanned rows into multiple partitions based on a few bits of the hash code for each group. For example, if we use lowest 8 bits of the hash code for each key, we'll have 256 partitions. Potentially, radix partitioning is prone to skew due to unlucky combination of keys and hash functions, but in real world, the probability of this is very small. With radix partitioning, our worker threads produce a number of hash tables. So in our example, each partial result consists of 256 hash tables instead of a single one. Each of the partitions combines all of these partial results, and together they contain isolated subsets of the final result. So we can merge them individually, independently, and in parallel. What's the most important? In the high cardinality case, our improved pipeline now looks like this. It involves a new parallel merge step. Once we've got partial aggregation results, we publish a merge task for each radix partition so that they are merged in parallel. This way, we get rid of the single-threaded merge bottleneck. This pipeline is exactly what we came up with. It's used for most group by and sample by queries that you can run in QuestDB. The pipeline is a bit more complex than the version 1.1 due to the optional radix partitioning steps, but it scales nicely in all scenarios. Another advantage is that radix partitions open up opportunities for further parallel steps. Say if we have order by and limit clauses in the query, we can apply the limit to each partition in parallel and then apply k-way merge to produce the final result. As you've already noticed, hash tables play a crucial role in parallel aggregation, so their performance cannot be underestimated. That's why we introduced specialized hash tables. All of our in-house hash tables use open addressing with linear probing due to their CPU friendliness. Depending on the group by column types used in the query, we choose the fastest hash table implementation. For instance, we have special hash tables for small fixed size keys such as 32-bit or 64-bit integers. So, what are the lessons we've learned in this journey? First of all, we're confident that a fast time series database must be good at analytical queries. ClickBench appeared to be a great starting point for us, certainly. Obviously, planning, focus, and discipline are required to make such noticeable improvements in a large query engine codebase. As a pleasant side effect, we've made sample by queries run parallel by reusing the same group by pipeline. And last but not least, we know exactly what we should improve next. That's it for today. Many thanks for joining the talk. If you have any questions around QuestDB and time series databases, don't hesitate to reach out to me. Have a nice day.